Okay, so I'll start with chapter 1, and today we'll discuss chapter 1 and chapter 2. Chapter 1, essentially, it's a very introductory chapter talking about the physics is based on the measurements, on our interaction with the nature. So after the long interaction with the nature, so the humans know what kind of law we have to use in order to describe behavior of the nature. And the phy207, actually, that course describes mostly mechanical motion. The most of the part is mechanical motion, and about a quarter of the course at the very end is a thermal property, which is also an interesting area, but quite apart from the mechanical motion. But that means that mechanical motion, Newton's law, which we're going to discuss, it's a main core of the course. All right. So during this course, and then you will have phy208, phy209. That course is related to some different property of the nature, like a wave property, optics, electricity and magnetism, quantum property, nuclear properties. All of these areas are used units to do the measurements, because essentially, what is a measurement? Measurement is when you try to quantify some certain property. For example, distance. You want to quantify this property, and in fact transfer this physical property into the number. For example, when you measure the distance using the ruler, and the ruler already had a units like inches or feet to measure the distance, then you can say that distance is like 5 feet or 2 inches. And when you start to operate with the numbers, it's a very effective way to process the information. Using the mathematics, you can multiply, add, divide, and so on. So the measurements essentially reduce that physical property to the numbers, and then you manipulate with the numbers. During the course 207, 208, 209, all of the 3 courses in physics, we will use specific system of units. It's named System International, SI, and in this System International units, we're using specific measure for the length, for the mass, time. Let me describe this property. So they, in some respect, may be different for some properties. For example, length, right? A. Length. So the length will be measured in meters. In meters. So that's abbreviation is M. That's the units. Oops, units for the become a little bit blurry. Let me switch off video and then switch it on. Okay. Yeah, sometimes it requires to do this procedure. Yeah, so it's different from what we usually using here in the United States. We're using inches or feet, but in System International, it's a meters, a meter. So the mass, another important physical property, mass. For the mass, we're using kilograms. Kilograms or kg. Time, right? Time. For time, SI units is seconds. Time in seconds. S, abbreviation S. And of course, since sometimes some property can be measured in different units, for example, in length can be measured in miles. So you have to be able to convert one unit to another, but it's not a purpose of that course to teach you how to convert, but just for your information. Usually what I'm in your problems, for example, in exam, mostly in the homeworks probably too, at least in exams, I'm not doing any exercise to convert one unit to another because it's a simple mathematical procedure. But just to demonstrate you, let's say 1 mile, how to convert. Let's say 1 mile, it's in meters, it's 1,609 meters. And question can be, if you have distance 5 miles, how many meters? How many meters in that distance? So to get the answer, you should multiply 5 times 1,609, and that is 845 here meters. So that's the one of the example of the conversion of the units. But as I said, it's you have to know and more or less understand how to do this, but it's not a main target of that course. Main target to give you some idea, basic knowledge about fundamentals law, which describes motion of the mechanical objects and relation between different physical properties. Okay, so now let me start with the so-called classical mechanics. So the classical mechanics, it's a part of the physics which describe mechanical motion of the macroscopic object. Like, for example, this eraser. So macroscopic object that contains, as we know, a lot of different molecules and atoms. They're moving inside this object. We cannot see that, but classical mechanics is a good approach to describe the mechanical motion of this object, reaction of this object on different forces, what's going to happen with this object if, let's say, force F applied. So, and how it will move. That's the subject of the classical mechanics. Of course, again, it's a little bit, become to be a little bit blurry, so let me switch it off and then on. Okay, so in order to describe the motion, we have to introduce first the parameters essential for the mechanical motion. And that part of the classical mechanic is named kinematic of the motion. Kinematic of the motion, it's the part which describes the main physical properties of the mechanical motion. So, okay, first topic, kinematic. Kinematics of the motion. And I will start with the one-dimensional case. Of course, in general case, we're living in a three-dimensional space. We have free degree of freedom of free coordinates, x, y, and z, to describe, let's say, position or velocity of any mechanical motion. But I will start for simplicity from a one-dimensional motion, and then we will come to the three-dimensional motion later on. So the first parameter to discuss is a position. Position. So since we're talking about one-dimensional motion, let me draw the reference frame, right? So this is my coordinate system. In order to mathematically describe the position, we have to introduce a coordinate system or reference frame with respect to which we're gonna measure the position. Let's say using the ruler, right? So any reference frame has an origin. So let's say this is my origin. So it's corresponds to the 0. It's origin of my coordinate system. Origin. origin. Okay, with respect to this origin, I will describe the position of the object and particular distance from that origin. A particular position will be measured, effectively transferred into some numbers. Let's say if I place the object here and then measure the distance L, or better to say not L, but X, this particular X. So that gives me idea about a position of the object, right? How I will do it? I'll take a ruler using a 1 meter as a reference unit for this ruler, and then I just measure how many meters I have between this point and that point, and then I'll get some number. Let's say 5 meters or 3 meters, 0.5 meters, depending on that distance X. So you see here in this procedure, I already use a ruler or some device in order to transfer the actual physical position of the object X into some number. And then later on, I will operate with this number using mathematics. Okay, the second property, displacement. So we know that macroscopic object, of this eraser can be moved from this position to that position, right? And up and down, left and right. Yes?
I just had a question. So for number 1 position, does the X represent, you know how you have the bracket? The X would represent the position, or like, which one would be the
X represent the position. And that position, as you can see here, if you go to the right, you see this, my reference frame has this arrow. That means that everything which is on the right, it will have a positive value, and everything on the left, this direction, from 0, will have a negative. So that's why the position may be positive or negative with respect to this origin of the coordinate system. So it's not a simple distance, because distance, it's a number which always positive. But position, the difference between position and the distance is that that position can be positive, like in this example, or if the object located on the left from the 0, that position will be negative. So when you're operating with the position, in that sense, you can add and subtract the position, but you will operate with the positive and negative numbers.
Okay, thank you, Professor.
Mm-hmm. So now the second property, displacement. Displacement. So we can, on this plot, we can displace this object from the position 1, let's say this is position 1, to position 2, to this position, let's say that's x2, right? So now this position is x2, right? So this x2. That's another position after displacement. So the displacement definition, we can write it delta x. It's the difference between x2 minus x1. Right. So the displacement on this plot is this segment. That's the delta x. As you can see here, because x2 is larger than x1, that delta x is positive. If you just subtract them, you'll see that it's going to be positive. But displacement can be negative, so I can move this object or this point to the left somewhere. And that, if I move it to the left, displacement will be negative. So again, you see that displacement can be positive or negative. That's one property. And another property is that when I compute the displacement, I am making difference between final position of the object, x2, and the initial position of the object, x1. Right? So the ordering is important here. Otherwise, you get an opposite sign. Do you have any questions regarding position and displacement? All right. So the next property I can introduce here is named average velocity.
Wait, I have a question.
Uh-huh.
So whenever you're writing down like position or displacement, you have to put a negative or plus sign next to the value.
When I'm writing expression for the displacement,
Not the, but the answer. Like when you find delta x, do you have to put like a plus sign or a negative sign?
yeah, absolutely. You have to here, let's say, yeah, you have to keep track of signs, definitely, because this x can be positive or negative. Let's say your initial x, for example, here, let's just example, here it's a 5, and here, for example, 8, right? So your x1 is 5, your x2 is 8, right? What is displacement? Delta x is 8 minus 5. So it's 3 meters delta x. But you may have a situation when let's say the object is not located at 5, but let's consider that x1 is still 5, but we move the object not to the right, but to the left, and let's say to this position. That is going to be x3, right? So we move this object from here to here. So now this, for example, minus 2. What's the displacement now between this initial position, this is the final position? So in this second case, what I will do, I will take my initial position, x1 is 5, but my final position, x3, right? That's my final position, x3 is minus 2. Then when I compute the delta x, I should write like this, minus 2, because this is the final position, right? This is the final, this initial, minus 2, minus 5, minus 7 meters. So now displacement in the second case is minus 7 meters. So again, you have to definitely keep track of the signs, just computing exact numbers here. Let's say if it's position 5, you write 5. If position minus 2, you have to use minus 2 when you do the computation. That's the essence of the manipulation. This, as you will see later on, x is a vector. It's a one-dimensional vector. So vector has a direction as in the magnitude. So when we will talk about two-dimensional motion, three-dimensional motion, you'll better understand. But for one-dimensional motion, the answer is you have to keep track of the signs here because it's a sign-sensitive entities, properties, both position, displacement. Now, did I answer a question?
Yeah, thank you.
I just
Yeah.
want to clarify. From 0 to x2, that is the position of x2, right?
Yes. From here to here, that's the position x2. You see that what I...
Okay, okay, got it. Thank you.
All right. Okay, so now the third property I would like to discuss is average velocity. What is the average velocity? Well, the velocity is a physical property which tells us how fast object moves, how fast in time it moves. High velocity means that object moves faster. Now, how to mathematically characterize this property? In order to characterize this property, you have to measure this property, right? How to measure this property? How to evaluate the velocity? So the average velocity is a good example of the property that requires measurements. All right, typically what we do, let's say if we're trying to measure velocity of some people who runs from this point to this point, we have a timer that requires, so to get a velocity requires a set of measurements. You have to start the timer at the beginning of the motion of the runner, right? and then you have to stop the timer at the final destination of this runner. So in this, if you want to evaluate average velocity of the runner, you have to do two measurements. First of all, measurements of the time at the initial state and at the beginning, and then time and the position at the very end. And then velocity you can find, you find the displacement of the runner during that time interval between start and finish, divided by the time interval for this process. Now, to formulate it mathematically, we can write that average velocity is displacement of the object delta x over time interval during which that displacement occur. In case of the runner, that time delta t is basically time between start and finish of the process. And delta x is displacement of this runner during the run. Okay, we can decompose it and run that. What is delta x? Delta x is x2 minus x1, and time delta t is time t2 minus t1. So the t1 is the time when you start your timer. Well, basically, usually t1 can be easily put to the zero, so that when you start your timer, and t2 when you stop your timer. So we'll see how many seconds it takes or hours it takes to complete this motion. So this is average velocity. So as you can see here in this formula, in order to get average velocity, you have to know four numbers: x2, x1, t2, and t1. And so that property characterized sort of, it's named average. So because we measure that property during a finite time interval. In that interval, for example, if you're not talking about the runner who's running in one direction only and just trying to go along the straight line, so-called, but you may have a much more complex motion. Let's say object may move back and forth before it will reach the destination point. Let's say, if you're talking about this example, so this point before reach this point x2, it may move up right and left several times, and then it will reach this point. So it may perform quite sophisticated motion. For the average velocity, from another hand, what is essential is just essential initial and final positions and initial and final times for the motion. That's why it's average. But often we want to know exactly what's the velocity of the object at this particular time, and that is property named instantaneous velocity. So let me remove this part, so we'll go to instantaneous velocity. Okay. So the fourth property, or maybe 3A property, instantaneous velocity. Instantaneous velocity. So that velocity is based on a certain mathematical procedure. And physically, what we in order to get instantaneous velocity, we have to reduce the interval between measurements of the time t1 and t2. So basically measure position or displacement of the object during the short and shorter time interval delta t. So in these formulas, we trying to reduce this delta t as much as we can. Of course, delta x will be also reduced. And what our experiment shows that in all cases related to the motion of the macroscopic object, like this eraser, this ratio actually tends to a certain value. Mathematically speaking, it means that this ratio has a limit, well-defined limit, and that limit in mathematics, it's named first derivative. So the position of the object, what we found from our experiment, is indeed, or displacement of the object, become to be smaller and smaller when we reduce time delta t. Now, when we will learn maybe later on some quantum mechanics, you will see that the motion of the macroscopic particle, such as electron, does not obey this property. So when you start to decrease time delta t, you may have some very unusual behavior. So this sort of formula are well applied to limiting formula, well applied for the macroscopic object. For the particle such an electron, you have to think about this, how to apply this formula. But since we're talking about the classical mechanics, which describe the motion of macroscopic object, that limit is well defined. Now let me write that. So the instantaneous velocity v at time t is a limit when delta t goes to the 0 of that ratio delta x over delta t. Right. And that ratio in mathematics, if that limit exists, is named first derivative. In the calculus, you learn different functions. So that functions has a different derivatives. And so what we know that the velocity is indeed first of macroscopic object is indeed the first derivative of the position x. Position x. All right. So we well, basically, if you have, let's say, position given, let's say position of the object as a function of time, for example, can be written as a 2 plus 3t minus 4t squared. Now, what is the velocity of the object? Let's say this is a position as a function of time here. It's written. What is the instantaneous velocity at t equals to 2? Well, this is an exercise from calculus. You have to find first derivative of this function. So velocity at time t is dx over dt. So now we have to take a first derivative of this expression. This is a constant, give us 0. That gives us 3. And that gives us minus 4 times 2t. Right, and then we're getting 3 minus 8t. And we have to evaluate this function at time 2 seconds. Right, so we have to evaluate at t equals to 2 seconds. So we just put t equals to 2 here and evaluate. So it's going to be 3 minus 8 times 2. So 16 minus 16 plus 3 minus 13 meters per second. So the velocity of this object, which moves in accordance with this formula at time 2 seconds, will be minus 13 meters per second. It's negative, meaning that if it, using this reference frame, as I said, this is our positive x. So the velocity at some position also can be computed here. What's the position here? At 4 seconds, more at 2 seconds, most likely it's going to be also negative. So that's the position object of this object somewhere here from the, that's approximately. So, and the velocity of this object will be directed this way, negative, minus 13. So the object will move this direction at that point, at that moment of time. Okay, so that's an example how to use the instantaneous velocity. So how to find the instantaneous velocity, especially it's easy if you know the position of the object over here. All right, and the last parameter, important kinematic parameter I would like to introduce and describe is acceleration. Well, before that, let me tell you that the velocity is actually indicate a rate at which the position changes in time. So if velocity high, that means that object moves fast, change of the position is very fast and large during time delta t. So it characterizes variation or rate of change of the position. But in principle, you may have a situation when the object moves with the velocity by itself may change in time. For example, in this example, if you see here that the velocity we found 3 minus 8t, so the velocity itself changing in time, so it becomes to be more negative and negative when the time growing up. So that means that object moves faster and faster to the left with the time. So that's a motion with the variable velocity. To characterize the motion with the variable velocity, there is another important parameter, which is named acceleration. Acceleration. Now that's the last kinematic property I would like to discuss.
Sir, I have a question. I noticed that the answer is negative 13 meters per second. What does the negative in this situation represent? Is it because, normally it wouldn't make sense for the instantaneous velocity to be negative. Does it indicate a direction here or?
Yeah, yes, that's what I draw here. You see, this is my reference frame. My positive direction in this reference frame is this, to the right. Everything to the right will have a positive value. Everything to the left is going to be negative value, right? So this is my origin. So position on the left from the zero is going to be negative position. That position, for example, here will have a negative value. But as we discussed at this position, velocity also directed opposite to this arrow. This arrow is directed this way, but velocity will be directed this way. You see that at this position, the object, it can move. It's moving along the straight line, right? It's a one-dimensional motion. It's like a train. Train can move this direction and move that direction. It cannot move perpendicular to the railroad. It's a one-dimensional motion, right? But this one-dimensional motion has two directions. So the object can move from the left to the right. If it's moving from the left to the right in this reference frame, then the velocity is positive entity. If it moves from the right to the left, like in this example, the velocity has a negative value. It's a negative velocity.
Thank you.
So the velocity, it's also similar to the position displacement. It has a positive, may have a positive or negative. It can be zero also values, because this property it's a vector. It has a direction. Let's say if you're talking about the position, let's say here, this position has a direction, so it's directed this way from the origin. So it is a vector. Okay, so now let me.
Professor.
Yes.
I'm sorry to interrupt, but so if it wasn't velocity, but if it was acceleration, it would have if it was negative, then it would have decreased the speed, so it would slow down, right?
Yeah. So the acceleration, it's another property which also can be positive or negative, and the relation to the velocity is not so kind of obvious. So you're right. You said that it describes rate of changing of the velocity, but that rate can be positive or negative. In other words, that rate can increase velocity or decrease velocity. So therefore, acceleration is also a vector, but it's not identical to the velocity. It's a different thing. It's a different property. All right. So the best way to think about that is it's a related, but it's a different property from the velocity, as well as, for example, position and the velocity. They're also somehow related, right? Because velocity is the first derivative of the position. They're related, but the particular relation is not so, well, it's straightforward, dx over dt, but let's say direction between this property is not so obvious. For example, let's say object is located here, right? It has a positive position because that position, displaced to the right from the origin of the coordinate system, so it's a positive position. But object here can move to the right, so it has a positive velocity, or it can move to the left, so it's negative velocity, or it just may stay here. In that case, velocity, if it's just stationary located here, in that case, velocity is 0, so it may have a different values. So despite the fact that velocity and position x are related through this formula, v equals to dx over dt, but the particular relation between signs of this and properties are maybe arbitrary. So it can be, for example, here x is positive and velocity positive. It's one possibility. Or it can be displacement can be positive, velocity is negative. It's another possibility, and so on. Right. So you have to make a separation between relation and actual, and the sign of these properties. They may be, despite the fact that they're related, this property related, but the sign may be different between them because it's just describe different properties of the motion. All right, so let me now describe acceleration. Acceleration, so this fourth property. Acceleration. Well, let me start with the average acceleration, A average. So I will use letter A for the acceleration. And so the average acceleration also is similar to the velocity, requires 4 numbers to compute. So it's the following formula. It's a V2 minus V1 divided by T2 minus T1. So here in this formula, V2 is the velocity of the object at time T2. V1 is the velocity of the object initial time T1. Let me give you example. Let's say objects start to move along this axis. So at this position, so it has the velocity V1, and then it accelerates, increase the velocity, and now at this position, it has velocity V2. And we measure this at time T2, T1, and that we measure at time T2. Right, so you see here that the velocity V2 is larger in magnitude and directed in the same way. So we have to just to measure this, measure that. That's an instantaneous value at this particular time. So we have 2 numbers and then divided by the time interval, which requires to change that velocity from V1 to V2. Again, in general case, V2 and V1 can be positive and negative. You have to keep track of that. So if the velocity V2, let's say, is negative, then you have to put minus here for the minus that value, actual value of the velocity. And similar to velocity, we can introduce instantaneous acceleration, and that's a limit when the delta t goes to the 0 of that ratio, delta v over delta t. Again, this ratio is delta v over delta t. Right? So we reduce and shrinking the interval between 2 measurements, but in any way, we have to do these two measurements in order to evaluate this acceleration, instantaneous acceleration. So that's the main kinematic parameters which we're going to use in order to describe the motion of the, okay, so this is a instantaneous acceleration. Instantaneous acceleration, that's this formula. Okay, so let's just give you example. Let's say object moves with the same 2 plus 3t minus 4t square. What is the acceleration of the object at time t equals to 2? Well, first we have to find velocity, and then, and I'm sorry, here, that this limit is apparently, it's a first derivative of the velocity versus time, right? First derivative versus time. So now in this example, what we want to find instantaneous acceleration at t equals to, let's say, 2 seconds. Similar to the previous example, but in the previous example, we want to find instantaneous velocity. Now let's find instantaneous acceleration.
Excuse me, Professor.
Yes.
What is that symbol next to dv?
Oh, this? It's
Yes.
a time, t.
Oh, okay,
So
thank you.
the velocity is a function of t. Well, I mean, you can remove it, dv over dt, if you feel more comfortable with that kind of notations. Yeah, because if the velocity does not depend on time, so acceleration is 0. So dv over dt is 0. All right, so let me find the instantaneous acceleration in this case. Well, first I will find instantaneous velocity because I need to find v, right, as a function of t. That's the first derivative of position, right? And if I take the first derivative, it's going to be 3 minus 8t. 3 minus 8t. And then I will use this formula to find the instantaneous acceleration. At equals to dv over dt. So then I'm taking first derivative from this expression. It's going to be minus 8 meters per second square. You see here that acceleration here has a fixed value, minus 8. So that acceleration does not depend on time. So it's the same at time t equals to 2 seconds, 5 seconds, 25 seconds. So this is actually, this formula describes a very important motion, very important for you, because that's the motion with the constant acceleration. Indeed, we just found that for this sort of dependence, the acceleration is indeed constant. In this case, it's minus 8. So that acceleration doesn't change in time. So it's the same. It's a motion with the constant acceleration. Now, if you look on this mathematical formula, you can easily recognize that why it's a motion with the constant acceleration, because this expression, mathematical formula, is a parabola, parabolic function. So there is no terms like 6t cubed, for example. These terms are absent here. Now, if you have this sort of t cubed, t4, and so on, and higher polynomial orders here, if you have that, that will not be motion with the constant acceleration anymore. It will be motion with the variable acceleration. So, but many motions, mechanical motions around us are motion with the constant acceleration. In particular, the projectile motion. That's why the case of the motion with the constant acceleration is a very special and very important. And my next topic is to describe motion with the constant acceleration. All right. Do you have any questions on the topics we just discussed? We discussed position, displacement, velocity, and acceleration. So there's four. Go ahead.
Professor, I just have a question. So I was thinking, so how velocity is like the derivative of position. In the same way with the acceleration.
Yeah, for the acceleration, you may use the second derivative of the position, because the velocity is the first derivative, and another derivative from velocity is going to be second derivative. So you can write that acceleration is the second derivative.
Yo, guys, it's getting boring, bro.
What do you want to do?
What do you take? What do you take?
Guys,
So would it, I just wanted to ask, so instant acceleration, would that be like the derivative of instant velocity?
yeah, it's the instantaneous acceleration. It's a first derivative of the velocity here.
Okay, got it. Okay. Thank you.
Let me mute all. All right. And now let me switch to the topic of the motion with the constant acceleration. Okay. Okay. Let me remove this. And let's discuss motion with constant acceleration. Motion with the constant acceleration. And let's first discuss case where we have constant velocity. That's a particular case. In that case, acceleration is 0, so it's constant. Constant velocity. Sometimes I can write this constant. When I write this v equals to constant, means that it's not changing with time. So for this motion, apparently if the velocity is constant, the average velocity will also constant. And we can write that for the, let's say v0 is constant. So now we can write, let's write the formula for the v0 using this average velocity result. So it's a x at time t minus initial position at time t0 divided by t minus t0, right? We can write this because this formula for the instantaneous velocity like this, because velocity itself is constant. So instantaneous and the average velocity in that case, the same. Right. So now from this ratio, we can see that x at position at moment t minus initial position x0 equals v0 times t minus t0. And we can...
Professor?
The screen is blurry.
Yeah. Let me. Yeah, all right. So, and therefore we can write that x at moment t can be written from this formula as x0 initial position plus v0 t minus t0. So this formula actually gives you complete description of the motion with the constant velocity. If you know initial position x0, velocity v0 at any moment time t, that gives you position of the object. Useful formula. Now let's just graphically represent this formula. So to represent this formula graphically, we should plot this position as a function of time. Okay, at time equals to the t0, that my time t0 here, the position of the object when the t equal to t0, this term is 0, the initial position of the object as 0, I will represent it here at this vertical axis. So the vertical axis represents position at time t. So at t0, we have this position x0, right? And then let's assume that v0 is positive. So then if it's positive and our x0 is also positive, so we should expect that position of the object will increase. So it will go up here. So let's say this is a time t. I would like to evaluate. So the position of the object will be displaced up and will be displaced uniformly in time. Okay, so this is the plot of that, which it's a straight line, as you can see here from this formula. So the displacement to delta x is equals to the v0 times delta t. So this position x at time t, and that interval, right, is a delta x, or this interval delta x equals to the v0 times t minus t0, right? And the position xt has a two parts. It's initial displacement, initial position x0 plus displacement delta x. The displacement delta x is v0 times t minus t0. All right, so now let me draw another plot. Another plot I would like to present here, dependence of the velocity as a function of time versus time. Well, in our case, the velocity is constant, so this is v0, and that's the t0 here, and then time t here. So velocity is constant. That's the plot of this dependence. Now let's find on this plot, let's find the area under the curve v equal to the 0. This area is this shaded area. This area equals base, which is, or height, which is v0, times the base, which is a t minus t0. Right? That's just simple result outcome from this plot. So that area under this curve is v0 times t0. And if we compare this area, this expression, with the displacement, we can easily see that for this motion, the displacement delta x equals to the area under the curve velocity versus time. The interesting, so we found this property just analyzing the motion with the constant velocity, but if the velocity is not constant, you'll still have this sort of relation between displacement during time delta t and the area under the curve v versus t. So to understand this relation, let me write some a little bit of. So what I'm trying to say that this relation delta x equal to the area valid for in general case, not necessarily case when the velocity v0 is constant. To understand that, we can write that velocity as a function of time is dx over dt, right? This is a definition of the instantaneous velocity. And from this formula, we can say that small displacement dx is v times dt. And now, if we integrate both parts of this formula from t0 to t, from t0 to t, then left side of this equation give us displacement delta x, but the right side of the displacement is indeed this integral from t0 to t vt dt. But this is an area. So geometrical meaning of the integral, it's an area under the curve. That's coming from the calculus. So that line indicates that this property we found from this simple consideration and comparison valid for in general case. Even if, let's say, object moves with not a constant velocity, but with variable velocity. Now I'm going to use this approach in order to evaluate the displacement for the motion with the constant acceleration, non-zero acceleration. So we'll use this formula to do this. Let me consider now case A constant. So acceleration is constant, and we can, if it's constant, we can write that acceleration, average acceleration, is velocity minus initial velocity divided by time minus initial time. So in this case, average velocity and instantaneous velocity must coincide because because acceleration is a constant. So from this formula, we can see that v at time t minus v0 must be equal a times t minus t0. And therefore, we can also write that velocity at any moment of time t is simply velocity at the very beginning, at the initial time, at t0, plus a t minus t0. So this is an immediate outcome from the fact that acceleration is a constant. So now let me now plot this function. So I'm plotting here. How velocity depends on time for the motion with the constant acceleration. So here I'm plotting velocity here the time t. All right, at t equals to the t0, which is this point, this moment of time, velocity is v0. It's v0. I will assume in this example, just for simplicity, that acceleration a is positive, has a positive value, so it will increase positive v0. So we should expect that the velocity will increase. So it's a real case of acceleration. In general case, that acceleration can be negative, so velocity will decrease in time. But let me consider a to be positive. So in that case, velocity will be uniformly increase in time. And at the moment t, I will have this velocity. And this is a straight line from velocity v0 to velocity v at moment t. Now, so that's how this plot represent this formula. So now this is this segment or sector is a times, it's a change of the velocity delta v, which is a times t minus t0. All right, now, as I said, I'm interested in the position. What is our displacement? What is the displacement for this motion with the constant acceleration? Right. So in order to find the displacement delta x, I will use this relation or this formula. So to find delta x, I have to find area under the curve v versus t. So I have to find this area. I can easily find the answer here just considering that this figure contains two well-defined figures. It's a right angle parallelogram. So I will use that figure to evaluate area A1. And then there is the right angle triangle. I will use the known formula for the area of the right angle triangles to get A2. So the area A here is sum of two areas, A1 plus A2. Now let's just look on this plot. A1 is V0, the height of this right angle parallelogram, times the base t minus t0. So A1 is a V0, t minus t0. That's the area of this right angle parallelogram. And then area of this right angle triangle A2, 1/2 1/2. So delta V, the height here, delta V, which is A times t minus t0, times the base, this is t minus t0. So that means that when I multiply it here, it's going to be squared here. And that area A must be equal to the delta x. So finally, if I write it here, delta x equals to this area. So I found the relation between displacement of the object moving with the constant acceleration A and the time t. So this is a formula. This is a very important formula. You should memorize it, remember it, write it down, and have access to this formula at any time during the exam, which is usually open book. Understand. All right. So now let me rewrite this. Delta x.
Professor, I have a question. How did you get the A2?
This t minus t0 in square?
Yeah, yeah.
Well, you see this right angle triangle? This one. You see that, right? So I'm evaluating area A2. So the area A2 is this height, which is A times T minus T0, right? This one. Times this base, which is T minus T0. And 1/2 is just a formula for the area of the right angle. So this is simply area A2. So when you multiply T minus T0 by T minus T0, you get T minus T0 in square.
Thank you, Professor. I got it.
Okay, so here I'm using the following, that let's say if you have a right angle triangle, this is A, this is a B. So then the area of this right angle triangle area is 1/2 A times B, right? So it's easy to understand this formula why it's 1/2, because if I add another the same triangle but just kind of tilt it a little bit, invert it, right? So now this area is twice larger than the area of the triangle, right? So this total area will be simply A times B, and the area of the triangle is going to be half of that, right? That's why we have this coefficient 1/2 here. That's coming from the formula for the area of the triangles. Oh, by the way, if you are not kind of familiar with different mathematical formula from algebra, from geometry, in the book we're using, there is appendix on the back. And in this appendix, there are a lot of different kind of formulas, including the formulas for the area of the triangles, definition of the sine function, cosine function, different kind of trigonometric relations, and also some formula from the calculus, like a first derivative, second derivative. So it's a good appendix. It's short, very condensed, and very useful specifically for this course. So I would advise you to look in appendix just to refresh your memory and your knowledge in algebra, elementary algebra, geometry, and so on. Okay, so now let me finish with this formula. So I will use for the delta x, I've been using that the displacement is a difference between final position at moment t minus the position at the very beginning at moment t0, that's x0. So if I use these two formulas, I can get the final result. Xt is position of the object at any moment time t for the motion with the constant acceleration a can be written in the following form. X0, it's the initial position of the object at the very beginning of the motion, plus V0 times t minus t0 at this part, and plus 1/2 a t minus t0 square, right? So this is a main result of our derivation. Often time t0 we can count as a 0, because let's say usually at the very beginning you just start your timer. At that moment time is 0, right? Now let's put time t0 equal to the 0. So in most cases that's what we have. In that case we get the following result. Xt is x0 plus v0t plus 1/2 a t square. Okay, this is a formula for the motion with the constant acceleration a. Now, what is essential to get the final result for the position of the object? You have to know initial position of the object x0, initial velocity v0. Initial velocity means that what was velocity of the object at position x0 at the very first moment, at 0 seconds. These two parameters, initial parameters describing this motion. and acceleration a. So you need three numbers in order to completely describe the motion with constant acceleration a. And this is a formula. Okay. All right. So let me discuss now this sort of construction is very useful to find a displacement of the object during the motion. Right. So I would like to last topic to discuss today is to use this sort of diagrams to evaluate or find some different property of the motion. So this formula.
I just
Yes.
want to ask one last question. Where it says T0 is equal to 0, you use the bottom formula when that's the situation?
Yeah. If you just put T0 equal to the 0 in this formula, so this term will disappear because it's 0, and this term will disappear, right? So you'll straight go to this. From this formula, you straight go to this formula.
Okay, got it.
Often it's more useful because it doesn't contain this initial time. You can easily put it to the 0, and then it's a less symbols here, easy to remember and to use.
Okay, thank you.
Yeah, and importance of this result is that, as I said, this formula describes motion of the object near the surface of the Earth, so-called projectile motion. We will discuss this motion in details next lecture, because in general case, the motion near the Earth is a three-dimensional motion. But here we discussed so far one-dimensional motion, only along the straight line. And that's why I would like to postpone this relation of this formula to the projectile motion for the next lecture when we discuss general three-dimensional motion. But you will see that this formula describes the vertical motion of the object, vertical component of the motion of the object for the projectile motion. So that vertical motion you can consider is just straight down or up. It's also one-dimensional motion. So, and that formula describes this motion with the constant acceleration, because that motion is indeed motion with the constant acceleration, and that has been established experimentally, of course, by Galileo Galilei, who measured that property of this motion. But as I said, we will discuss this implementation of this formula next lecture. Today, I would like to discuss last topic. It's application of this sort of geometrical meaning of the integrals or analysis of the motion using the areas. You will see that this geometrical approach is very effective even for some quite complicated motions. So what I would like to discuss is the motion with the variable acceleration, but it will be kind of can be segmented on the motion with the constant acceleration. Let me now make a plot of velocity as a function of time versus time. And let's consider the following motion. Say 10, 20. So units for the velocity is meters over the second, right? Because the velocity is delta x over delta t. So this is meters and time in the second, so meters per second. And for acceleration, it's the meters per second square units, SI units. Okay, so here I'm plotting versus time, and let's say this is a 10, 20, 30 seconds. And let's assume that we have the following motion. So the first 10 seconds, object moves from the velocity, accelerates from velocity 10 meters per second to 20 meters per second to this point, with the constant acceleration like this. And then next 10 seconds, the object moves with the constant velocity 20 meters per second. And that's the other part of the motion. And finally, it decelerates its velocity toward the zero during the next 10 seconds. So it just goes like this. So it's one possible motion, and I represent here how the velocity for this particular kind of motion depends on time. You see there are apparently 3 segments here. First, object accelerates, then it moves with the constant velocity, means acceleration is 0, and then it decelerates towards the 0. And looking on this plot, there are a few questions can be asked here. Our first question, A, what is the average acceleration of the object between time 0 and 15 seconds? What is the A average from T0 equal to the 0 to T equals to 15 seconds? So apparently you see here, so we're considering the motion between 0 and 15 seconds. So you see here that the velocity changes. So apparently during this time interval, there is acceleration, and we want to find what is the average acceleration here. So the average acceleration can be found using the, again, formula, which we discussed. So it's a velocity at time t 15 seconds minus velocity at time 0 seconds divided by time interval 15 minus 0. Okay, so what I'm using here, I'm using this formula that A average is V2 minus V1 divided by T2 minus T1. We discussed it at the beginning, right? So here I'm just implement this formula, and we have to find the particular numbers here. What is the velocity at the final, at the point, at the time 15 seconds? So this is the velocity. So it's a 20 meters per second. So it's a 20. What is the velocity at time 0? It's a 10 meters per second. So minus 10 divided by 15 minus 0 is 15. So it's a 10 over 15. Then we can simplify, it's going to be 2/3 meters per second squared. So that's the answer for the average acceleration. We found it's a 2/3 meters per second squared. Well, apparently, depending on the, it's a 15, you may compute it for any time interval, let's say for 12 seconds, for 17 seconds, for 25 seconds. So when you do this, you just need to, let's say for 25 seconds, it's going to be somewhere here. In the between, looks like for 25 seconds, average acceleration will be 0, right? Because that V2 here corresponding to this point, 25, is going to be around 10. It's going to be not around 10, it's going to be 10. So what I'm trying to say that depending on time t, average acceleration will be different. So we found it for this particular case for time interval between 0 and 15 seconds. All right, so relevant question for this diagram is also question B. what is the instantaneous acceleration at t equals to the 5 seconds, right? So at this point, at this moment of time, 5 seconds, what's the instantaneous acceleration here? So here, to answer on this question, you have to understand meaning of the instantaneous acceleration. It's a first derivative of the velocity versus time, right? What's the first derivative of the v versus t at this point? It's basically slope of that straight line, right? So if you look here, then dv over dt is a slope of this line. Now, in order to get answer here, you have to find that slope. And that slope is simply delta v over delta t. And let's say that my delta v, and that is my delta t. So you can see here that to evaluate the slope, we can say that that delta v is 20 minus 10 divided by delta t. Delta t is 10, so 10 minus 0. So we got this 10 over 10. So it's simply 1 meter per second squared. So the acceleration at the time t equals to the 5 seconds is 1 meter per second squared. And this acceleration is a constant because slope at this position, at this moment of time, slope at this moment of time are the same. So this segment from 0 to 10 represent motion with the constant instantaneous acceleration 1 meters per second square. And indeed, during the 10 seconds, it increased the velocity by 10. Okay, so we found the answer 1 over meter over second square, instantaneous. Now, relevant question, for example, also, what's the instantaneous acceleration at this point? At t, 25 seconds. So the conceptually is the same equation as here, but in order to get the right answer here, you have to take into account that the slope here is negative. So here slope positive, velocity goes up. So here the slope negative. Velocity goes down, meaning that acceleration should be negative. But the answer can be found from this formula for the motion with the constant acceleration. Let's say to find the slope here. Slope is minus, well, that value is 20 divided by this time interval is 10 minus 2 meters per second square. So the instantaneous acceleration at this moment of time is minus 2 meters per second square.
So that's deceleration.
That's a deceleration, but you can say negative acceleration, positive acceleration. So yeah, you may name it deceleration. Velocity decreases.
Thank you.
All right, so the last question here I would like to answer is that what's the displacement of the object during the 30 seconds? So the total displacement for this motion. Okay, the answer on this question, the displacement. So the displacement for this whole time interval is just area under this figure. And that area can be, again, disassembled to several parts. Let's say this is A1, area of this right angle triangle. This is A2, A3, and A4. Or if you know some other approach to get this area, you can use it. So I'm just disassemble this on this total area on 4 pieces, and for each piece I can easily write. So here, for example, so total displacement is the sum of these 4 areas. And now let me write. So the area A1 is 1/2. The base is 10, height is 10. So 10 times 10 plus area 2 is 10 by 10. Area A3 is 10 by 20. And area 4 is 10 by 20 times 1/2. And then that gives me 50 plus 100 plus 200 plus that gives me 100. Now this 450 meters. So the total displacement for this motion is 450 meters. Okay, guys, we're done for today. Do you have any questions?
How did you know how to divide the areas? Like to split them?
How do I know? I can recognize some geometrical figures like this right angle parallelogram. So I know that area of the A3 is 10 by 20, right? So I know that. So that's how I divide that.
Okay, thank you.
Right. So, and this is a right angle triangle. But some of you may remember formula for this kind of figure. You can use just this as a one area and find this area. But there are many ways to get the answer, right? So I think that this segmentation looks natural. So because I divided on the right angle triangles and right angle parallelograms, and the area of these figures are easy to evaluate. Okay, any other questions? All right, guys, so see you next week. So I'm stopping recording. Stop